On the infinitesimal scale, the building blocks of our material world reveal a surprising simplicity. Solid-state physics and chemistry primarily deal with just two types of particles: the nuclei composing the periodic table, and the electrons. Their interaction is predominantly governed by electrostatic forces, with magnetic influences playing a minor role except in rare instances. This simplicity, however, belies the complexity lurking within. The Schrödinger equation, or its relativistic counterpart, the Dirac equation, is at the heart of understanding these particles. It elegantly describes their behavior. The main point of it is to calculate the energy eigenvalues of the Hamiltonian operator, the energy operator. It does so by finding the so-called wave function of the particle in the system. These are the solutions of this partial differential equation. Of course, if you've already taken a course in quantum mechanics, you must have encountered simple problems like the particle in a box, the potential barrier, and the harmonic oscillator. These are all single-particle problems. The Schrödinger equation is a jewel of quantum mechanics. Yet, its practical application encounters a formidable barrier, known as the exponential wall, as the great physicist Walter Kohn once described it. Let's see why this wall is so high and even exponential. To grasp the magnitude of this wall, consider the wave function of something as seemingly simple as a nitrogen molecule N2, comprising 2 nuclei and 14 electrons. The Schrödinger equation for such a system is a partial differential equation in a staggering 3n dimensions, where n represents the number of particles. Visualize expressing this wave function on a grid with roughly 100 points along each spatial direction. Also, don't forget to consider 2 spin states for each of the 14 electrons. The resulting data set would consist of approximately 10 raised to 100 complex numbers. I don't know what is this number called. A Google or something? To put this into perspective, a data server capable of storing this amount of data, composed of current terabyte hard disks, would span a volume with a diameter of 10 billion light-years. This is really an exponential wall. So yes, the theory is way advanced than current technology. With all these computational impossibilities, we have to find another way to use quantum mechanics and measure the energy of systems. We set up a new kind of equations. First, let's look at the Hamiltonian itself. This is the entire form of it. From left to right is the kinetic energy of the nuclei, the electron's kinetic energy, the nucleus-nucleus interaction, the electron-electron interaction, and finally the electron-nuclei interaction. Here are also the explicit form of each of these terms. But don't worry, things are not gonna get mathy. Hence, we can define 2 Hamiltonians, the nuclear and the electronic, separately. But as we can see, the nuclear part contains an electronic energy term that depends on the nuclei coordinates. The electronic Hamiltonian contains a term that depends on the coordinates of the nuclei as well. Therefore, the first great approximation we do here is that we assume that the nuclei are fixed as classical objects in the background. The positions of these nuclei become ordinary coordinates, and not quantum mechanical operators anymore. Well, a nucleus or an ion is at least 2,000 times more massive than the electron, so regarding them fixed in the time scale of the fast-moving, light and highly quantum mechanical electrons is justifiable. This procedure has a name, it's called the Born-Oppenheimer approximation. Yes, the same Oppenheimer. Second, we dump the idea of directly finding the wave function, because it's just an extremely difficult task to do, and define instead the density function. This is the delta function of the electron's positions. Notice that they are really quantum operators. If you remember some quantum mechanics, then the density operator is really defined by the single electron's wave functions. If it's the density of the ground state, then these wave functions will also be those of the ground state. Now we move a step further, and it will be our last step. We assume 2 theorems. The first one says V sub En is a unique functional of the ground state density. The theorem is provable. But I'll skip it to help you focus on the idea itself. However, I encourage you to read the proof. A high school student can understand it. The second theorem says, the total energy functional of the electronic density is minimum for the system when the density is that of a ground state. This is provable as well, and surprisingly both proofs are not even long. And so, we have these 2 provable statements that will allow us to break down the problem into a doable numerical one, and to find the ground state energy of the studied system. This whole thing has a name, it's called or it set the basis of the density functional theory. This is how the problem looks like now. Now to the last part of this video. Since the electrons interact with each other as quantum particles, then the kinetic energy of each one of them can be split into two contributions, the expectation value of the kinetic energy as a functional of the density, and an extra term that is also a functional of the density, but it's unknown. It's called the kinetic correlation term. No one knows how this term looks like. Also, the term of electron-electron interaction contains a Coulomb interaction term, and in addition a purely quantum mechanical term called the exchange term. This is due to the fermionic nature of electrons, and once again, no one on Earth knows what form it really has. So we sum up these two unknown terms of energy into one term called the exchange correlation term. This part is really unknown, and can only be approximated to get the ground state energy of the system. Kohn and Sham put forward a way to deal with it. They assume that electrons do not interact with each other, but rather they move in an external total potential, now called the Kohn-Sham potential. And the energy is then. So, the energy of the system is now this sum with the Kohn-Sham potential. I encourage you to check out the proofs of the theorems. The calculation algorithms are also available, and I might go through those in another video. I hope you now have some insight into the practical aspects of quantum mechanics, such as studying molecules and solids, and how far we are from being able to directly apply the Schrödinger equation to them. That's it for this video. Please consider following the channel and check out the other videos. Thanks for watching.